May 11th, 1945. The waters off Okinawa, Ryukyu Islands. Radar operator Seaman First Class Robert Johnson hunched over his glowing screen aboard the destroyer USS Hadley, watching dots multiply across the phosphorescent display like a plague spreading across green glass. 156 incoming aircraft, all Japanese, all committed to dying. Johnson had been tracking enemy raids for 8 months across the Pacific. Nothing had prepared him for this. The kamikazes were coming in waves, staggered altitudes, from multiple vectors simultaneously. A coordinated assault designed to overwhelm American defenses through sheer numbers and the terrifying mathematics of suicide tactics. In the gun director above him, Fire Controlman Second Class James Foster was making calculations that would have seemed like science fiction just 3 years earlier. His 5-inch guns were loaded with shells containing technology the Japanese High Command had concluded was physically impossible. Miniature radio transmitters packed inside artillery rounds, electronics designed to survive 20,000 times the force of gravity, vacuum tubes that functioned after experiencing acceleration that should have shattered them into powder. Each shell would detonate automatically when it sensed an aircraft within lethal range. No human timing required, no manual fuse setting, no guesswork about where a target would be in 15 seconds. The weapon did the thinking. The shell made its own decision about when to explode. Over 90 minutes of continuous combat that morning, Hadley's guns would fire proximity-fused shells at rates that consumed ammunition faster than loaders could feed the magazines. The ship would shoot down 23 Japanese aircraft before being struck by 4 kamikazes that penetrated defenses already overwhelmed by unprecedented numbers. But Hadley would survive. Without proximity fuses, the ship and her entire crew would have been obliterated in the first 30 minutes. The story of how American 5-inch guns became autonomous plane killers, capable of engaging targets at 3 miles, began not with Navy admirals or Pentagon strategists, but with a volatile physicist in a converted Chevrolet dealership in Silver Spring, Maryland, who in the summer of 1940 was told to solve a problem every major military power had concluded was impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem was stated simply enough that it could fit on a single sheet of paper. German and Japanese aircraft were decimating Allied ships and ground forces. Conventional anti-aircraft guns required either a direct hit, extraordinarily difficult against targets maneuvering at 300 miles per hour, or a timed fuse set to explode at a predetermined altitude based on calculations about where the aircraft would be when the shell arrived. In practice, at the start of the war, destroying a single enemy aircraft required approximately 20,000 shells. Some estimates ranged as high as 100,000 rounds per kill. The ammunition expenditure was unsustainable. The casualty rates were catastrophic. Ships were being sunk, bomber formations were being massacred, cities were burning. The concept of a proximity fuse had existed for decades. Build a fuse that could detect when it approached a target and detonate automatically. Simple, in theory. Impossible in practice, given the technology of the 1930s. Germany had explored proximity fuses as early as 1930, developing over 30 different designs. Acoustic sensors that would trigger on engine noise, electrostatic detectors that would respond to charged aircraft surfaces, photoelectric cells that would react to changes in light. By 1939, after nearly a decade of research, German engineers had concluded that technical challenges were insurmountable. The acceleration forces were simply too severe. When a 5-inch shell is fired, it accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This creates a crushing force of 20,000 times Earth's gravity. Every component inside the shell experiences stress equivalent to being hit by a sledgehammer traveling at supersonic speed. Then the shell spins at 25,000 revolutions per minute as rifling imparts stabilizing rotation. The centrifugal forces tear apart anything not perfectly balanced. Temperature inside the gun barrel reaches over 5,000 degrees Fahrenheit for the milliseconds of acceleration. And after surviving this violence, the delicate electronics had to function perfectly during the few seconds of flight time before reaching the target. German technical specifications concluded that vacuum tubes, the only electronic amplifying devices available in 1940, could not possibly survive artillery launch. The glass envelopes would shatter, the internal filaments would break, the carefully aligned electrodes would shift out of position. Even if somehow the tubes survived being fired, the shock of setback would destroy the delicate circuits. Adolf Hitler's leadership, prioritizing projects that could reach production within 6 months to support the coming invasion of the Soviet Union, formally cancelled Germany's proximity fuse programs in 1940. The files were archived, the prototypes were stored. Rheinmetall Borsig would resume limited work in 1944, far too late to affect the war's outcome. The British had pushed further. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a miniature Doppler radar system. They built prototypes for rockets, which faced far less severe acceleration than gun-fired shells. Tests showed the concept worked under ideal conditions, but Britain's program was stymied by 2 critical obstacles. The cost was astronomical. Each prototype fuse required hand assembly by skilled technicians working under microscopes. Britain's industrial capacity was already stretched to breaking point building fighters, bombers, and radar stations. Diverting resources to develop an experimental fuse that might not work seemed impossible to justify. More fundamentally, they could not solve the miniaturization problem. The smallest vacuum tubes available in 1940 were those used in hearing aids. These tubes were perhaps 1 inch tall and weighed a fraction of an ounce. They were designed for the gentle environment of sitting in someone's pocket, cushioned against occasional drops or bumps. When British engineers tested hearing aid tubes in artillery shells, every single tube shattered on firing, not damaged, not cracked, completely pulverized into glass fragments and twisted metal. The forces were simply beyond what any vacuum tube could survive. By 1941, British scientists had working prototypes that functioned perhaps 50% of the time under laboratory conditions. For military use, this was completely inadequate. A weapon that failed half the time was worse than no weapon at all, because it consumed resources while providing unreliable results. The British shared their research through the Tizard mission when America entered the war. But it would be American scientists and American industry that actually made it work, not a laboratory curiosity that functioned sometimes under perfect conditions. A mass-produced weapon that could be manufactured by the millions and worked reliably in combat. Dr. Merle Anthony Tuve, born in Canton, South Dakota, educated at the University of Minnesota and Johns Hopkins, had spent his career exploring the physics of the ionosphere using radio waves. In 1925, working with Gregory Bright, he had pioneered techniques for measuring the reflection of radio waves from the ionosphere to map its structure. This work laid theoretical foundations for radar. When the National Defense Research Committee, formed on June 27, 1940, under the direction of Vannevar Bush, approached Tuve about developing a proximity fuse for artillery shells, he understood immediately that radio physics might provide the solution that had eluded everyone else. Tuve was brilliant but volatile. Colleagues described him as demanding, impatient, and absolutely unwilling to accept that anything was impossible. When told that miniature electronics could not survive artillery acceleration, his response was characteristically blunt. "Then we will build electronics that can survive." Section T, as Tuve's group was designated, began operations on August 24, 1940, with a handful of researchers in a laboratory at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, District of Columbia. Their first challenge was determining what components a working fuse would require. A radio transmitter capable of operating at frequencies that would provide usable Doppler shift when reflected from aircraft. A receiver sensitive enough to detect signals reflected from targets several hundred feet away. An electronic amplifier to boost the received signal to usable levels. A circuit to compare transmitted and received frequencies and detect the Doppler shift that indicated proximity to a target. A power source that could provide sufficient voltage and current in a package small enough to fit inside the fuse. A detonator triggered by the electronic circuit when Doppler shift reached the predetermined threshold. safety mechanisms to prevent premature detonation from radio interference, shock, or the ship's own radar. All of this had to fit inside a space approximately 8 inches long and 2 inches in diameter, leaving room for 7 pounds of high explosive in the shell body. The budget was brutally constrained. The fuse could weigh no more than 2 pounds. Every component had to be miniaturized beyond anything that existed in industrial production. WWII settled on a radio-based system operating at approximately 180 to 220 MHz. A miniature transmitter in the nose of the shell would emit continuous radio waves. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect, the same phenomenon that makes a train whistle change pitch as it passes. When the reflected signal reached a predetermined frequency shift, indicating the target was within lethal range, an electronic circuit would close and send current to a detonator that would explode the main charge. The shell would destroy itself at the optimal moment for maximum effectiveness against the target. The theory was elegant, the mathematics were sound. Making it work was another matter entirely. James Van Allen, a young physicist who would later discover the radiation belts surrounding Earth, joined the Applied Physics Laboratory at Johns Hopkins in April 1942 as a founding member. He faced the task of developing what the team called ruggedized vacuum tubes that could survive forces that destroyed every existing tube design. Van Allen started with miniature tubes that Raytheon and Sylvania had developed for hearing aids. These represented the smallest vacuum tubes in production anywhere in the world. Each tube was roughly 3/4 of an inch tall and weighed less than 1/10 of an ounce. Inside the glass envelope, a filament heated by electrical current emitted electrons. These electrons flowed through a vacuum toward a plate, with their flow controlled by grids that acted as switches and amplifiers. The design was exquisitely delicate. The filament was thinner than a human hair. The grids were fine metal mesh suspended by thin wires. The glass envelope was made as thin as possible. To minimize weight, everything about the tube's construction prioritized miniaturization and efficient operation in gentle conditions. When fired from a gun, these tubes shattered instantly. The glass cracked, the filaments snapped, the grids collapsed. Van Allen needed to redesign every aspect from first principles. Working with Sylvania Company engineers, he began systematically strengthening each component. The glass envelopes were thickened and carefully annealed to remove internal stresses. The internal filaments were redesigned with shorter spans and heavier cross-sections. Instead of being stretched between supports, the filaments were coiled tightly and embedded in shock-absorbing materials. The grids were redesigned with heavier gauge wire and shorter unsupported spans. The electrode structures were spot-welded rather than crimped, creating mechanical bonds that could withstand extreme stress. The entire tube assembly was potted in wax inside the fuse body, which cushioned the tubes against shock while providing electrical insulation. Every iteration had to be tested by firing complete fuses from a vertical gun into the ground at the Naval Proving Grounds in Dahlgren, Virginia. The soft earth caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see what had broken. The testing process was brutal and methodical. Fire a prototype, recover the shell, disassemble the fuse, examine every component under magnification, document failures, redesign, build new prototypes, repeat. Each cycle took days. Each improvement was measured in small increments. Through hundreds of test firings and thousands of design iterations, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. Half the tubes survived firing and functioned during flight. Half failed, either shattering on launch or malfunctioning due to damage. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during the production ramp-up. They were right. By early 1943, reliability had climbed above 90%, but vacuum tubes were only one challenge among many. The fuse needed a power source that could provide sufficient voltage to operate the radio circuits. Conventional batteries were too large and had limited shelf life, particularly in tropical heat, where temperatures inside ammunition magazines could exceed 120 degrees Fahrenheit. Harry Diamond and Wilbur Hinman at the National Bureau of Standards developed an ingenious solution: a reserve battery that used liquid electrolyte kept separate from the battery plates until activation. The battery consisted of a glass tube filled with electrolyte solution, sealed with metal plates at each end. When the shell was at rest, the liquid remained in the center of the tube, isolated from the metal plates by air gaps. No chemical reaction occurred. The battery generated no power. This gave the battery indefinite storage life, immune to temperature variations or gradual discharge. When the shell was fired, centrifugal force from the shell's spin forced the electrolyte outward against small pieces of magnesium and silver chloride embedded in the tube walls. Chemical reaction between the electrolyte and metal plates generated electricity. The battery activated only when the shell was spinning, providing a built-in safety mechanism that prevented premature detonation while the shell was being handled or stored. The fuse needed multiple additional safety mechanisms. It could not arm until well clear of the gun, ensuring it would not detonate if there was a malfunction during firing. It required protection against accidental detonation from radio interference or the ship's own radar systems, which operated at similar frequencies and might trigger the fuse prematurely. It needed wave suppression circuitry to prevent premature detonation when fired at low angles over water, where reflections from the ocean surface could trigger the Doppler detector before the shell reached its target. Each safety feature added complexity, additional components, more potential failure points. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components. The Mark 32 fuse for the Navy's 5-inch gun was 8 inches long and weighed just over 2 pounds. Inside its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942. More complex than any radio receiver, more rugged than any military equipment, more precisely manufactured than any mass-produced electronic device. Each fuse represented the absolute cutting edge of what 1940s technology could achieve. On August 12, 1942, the light cruiser USS Cleveland conducted the first operational test in Chesapeake Bay. The target was 3 radio-controlled drone aircraft flying patterns designed to simulate attacking enemy planes. Using conventional time-fused ammunition, downing these maneuvering drones typically required dozens of shots from multiple ships firing coordinated salvos. Cleveland's gunners, firing proximity-fused shells for the first time, destroyed all 3 drones with just 4 bursts on the first day of testing. The Navy immediately cancelled the remainder of the scheduled tests and ordered mass production to begin without waiting for additional validation. 5 companies were selected to manufacture the fuses: Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Each company received detailed specifications, manufacturing drawings, and orders to begin tooling for production, measured in tens of thousands of units per month. Production started slowly. The manufacturing processes were complex, requiring specialized equipment and trained workers. Quality control was absolute. Every component had to meet specifications measured in thousandths of an inch. Every tube had to be tested electrically before assembly. Every completed fuse had to pass functional tests that verified all circuits operated correctly. By the end of 1942, factories were producing 500 fuses per day, but American industrial capacity was just warming up. By late 1943, production had reached 40,000 fuses per day. At peak output in 1945, production exceeded 70,000 fuses daily. Over the course of the war, American industry produced more than 22 million proximity fuses at a cost exceeding $1 billion 1940s dollars. More than 100 factories participated in some phase of production, from manufacturing individual components to final assembly and testing. The Crosley Corporation in Cincinnati alone produced 525,913 fuses, representing 24% of total production. The company employed 10,000 workers operating continuously, 7 days a week, 3 shifts per day. At peak output, Crosley was completing 16,500 fuses daily. Sylvania Electric Products in Ipswich, Massachusetts produced even more, manufacturing 568,332 fuses, while also producing 95% of all miniature vacuum tubes used across the entire program. The company's workforce peaked at 12,000 employees working around the clock. Thousands of workers, many of them women entering industrial employment for the first time, assembled the intricate components under conditions of absolute secrecy. Workers signed security oaths acknowledging that disclosure of information would constitute treason. They were searched entering and leaving the facilities. Personal belongings were inspected. Conversations were monitored. They did not know what they were building. Component manufacturers produced parts without understanding their purpose. Assembly workers put together sub-assemblies without seeing the final product. Only a handful of supervisors at each facility knew they were building fuses for artillery shells. Security surrounding the proximity fuse was second only to the Manhattan Project developing atomic weapons. The device was given the deliberately misleading code name VT fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. Documents referred to POSIT without explaining what the term meant. The very existence of the fuse was classified above top secret. Even its use in combat was initially restricted to situations where there was absolutely no chance of a dud falling into enemy hands. The Pentagon feared that if Germany or Japan obtained an intact fuse, their engineers might reverse engineer the technology or develop countermeasures. If Germany equipped its anti-aircraft guns with proximity fuses, American intelligence analysts estimated bomber losses could increase by 300%. The strategic air campaign against German industry might become impossible to sustain. If Japan developed proximity fuses for anti-aircraft guns defending the home islands, casualties during any invasion would be catastrophic. So the fuses were used only over water, where dud shells would sink beyond enemy reach. When a dud proximity-fused shell landed on Sicily during the invasion in July 1943, headquarters dispatched a special patrol with orders to recover it before German forces could find it. The patrol succeeded, but the incident reinforced the absolute prohibition against land use. The first combat use came on January 5, 1943 off Guadalcanal in the Solomon Islands. 4 Japanese Aichi D-3, a dive bombers, Allied code name Val, attacked a United States Navy task force escorting transports. The Japanese pilots dove through anti-aircraft fire, released their bombs, and turned away with characteristic precision. As the aircraft broke off their attack, Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on the cruiser USS Helena, fired 3 salvos of proximity-fused shells at the departing bombers. All 3 shells exploded near one of the aircraft without direct hits. The aircraft, shredded with shrapnel, trailing smoke and flames, plunged into the sea. Helena's gunners had achieved what would have required dozens or hundreds of conventional shells. They had downed an enemy aircraft without scoring a direct hit, without perfect prediction of the target's course, without manual fuse setting calculated to explode at exactly the right altitude. Word of the success spread rapidly through the Pacific Fleet. Ships that had received proximity fuses began using them in every engagement. Cruisers, destroyers, and battleships reported kill ratios far exceeding anything achieved with time-fused ammunition. Gunnery officers who had struggled for months to achieve occasional hits were suddenly downing aircraft with single salvos. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. The 3-to-1 effectiveness advantage translated directly into saved ships and saved lives. Admiral Arleigh Burke, later Chief of Naval Operations, recalled that when he served as Chief of Staff to Admiral Mark Mitcher commanding the fast carrier task forces, proximity fuses knocked down enemy planes by the dozens. Ships that previously required concentrated fire from multiple vessels to down a single aircraft were achieving kills with individual gun mounts. The psychological impact on Japanese pilots was immediate and profound. They reported that American anti-aircraft fire had suddenly become impossibly accurate, Shells seemed to explode whenever aircraft approached, regardless of maneuvering or altitude changes. Pilots who survived attacks described explosions that appeared to track their movements, detonating precisely when aircraft came within range. Japanese tactical doctrine began to change in response. Attack profiles shifted to higher altitudes, sacrificing bombing accuracy to remain outside effective range. Torpedo bombers approached at wave-top altitude where radio reflections from the ocean surface caused some proximity fuses to detonate prematurely. Dive bombers released at steeper angles to minimize exposure time. These adaptations reduced strike effectiveness while failing to restore the advantage Japanese aviation had enjoyed earlier in the war. American ships continued to shoot down Japanese aircraft at rates that made conventional attacks increasingly suicidal even before the formal adoption of kamikaze tactics. But for most of the war, the Pentagon strictly forbade use of the fuse over land. The risk was too great that a dud shell would fall into enemy hands. The security classification remained absolute. Use was restricted to naval combat in open ocean, where duds would sink to depths beyond any salvage capability. This absolute security restriction began to crack in June 1944 when Germany unleashed the Von flying bomb against London. Launched from sites across the English Channel, the V-1s approached at speeds of 400 miles per hour, faster than many Allied fighters. Small, fast, and arriving without warning, they were extraordinarily difficult to intercept. The pilotless missiles were essentially cruise missiles decades before that term existed. A pulse jet engine provided propulsion. A simple gyroscope maintained heading. A mechanical counter driven by a propeller measured distance traveled. When the counter reached the preset value, the engine cut off and the Von dove toward its target, carrying 1,850 pounds of high explosive. From June to late August 1944, Germany launched over 9,000 V-1s against Britain. The missiles inflicted tens of thousands of civilian casualties. Entire neighborhoods were destroyed. The psychological impact was severe. Unlike bomber raids that came at predictable times and could be defended against by fighters, V-1s arrived randomly throughout day and night. British defences initially could destroy only 17% of V-1s that entered the coastal gun belt. Fighter aircraft shot down some. Anti-aircraft guns using conventional time-fused ammunition destroyed others, but the majority penetrated defences and struck London and surrounding areas. The situation was desperate. Prime Minister Winston Churchill personally authorised use of proximity fuses in anti-aircraft guns defending Britain, overriding the security restrictions that had kept the technology out of German hands for 2 years. The decision was agonising. If Germany captured intact fuses and reverse-engineered the technology, the consequences could be catastrophic. But the Von campaign was already catastrophic. Thousands of British civilians were dying. Churchill decided the immediate threat outweighed the long-term risk. Modified fuses were rushed into production, specifically calibrated for the small, fast V-1s. Crosley Corporation in Cincinnati received urgent orders to modify production specifications. Fuses normally calibrated to detect large aircraft with significant radar cross-sections needed adjustment to trigger reliably on V-1s, measuring only 25 feet in length with minimal metal surfaces. British and American anti-aircraft guns along the coast were equipped with proximity-fused ammunition, working in conjunction with new radar systems and fire control computers. Guns were repositioned to create a concentrated belt along the coast, where V-1s crossed from France into England. Every gun in the belt was fed proximity-fused ammunition exclusively. The effect was dramatic. Within 4 weeks, the destruction rate climbed from 17% to 74%. By late August, 82% of incoming V-1s were being shot down. During one day in late August, anti-aircraft guns destroyed 97 V-1s out of 104 detected by radar. Churchill later stated that the proximity fuse made possible the successes that anti-aircraft command was obtaining against Von flying bombs. The campaign demonstrated beyond doubt that the proximity fuse was war-winning technology, but it also meant the secret was partially compromised. Thousands of fuses were being fired over land. Duds were falling in fields and forests across southern England and northern France. Recovery teams worked frantically to locate and secure every dud before German forces could find them, but the risk that had seemed unacceptable in 1943 now had to be weighed against overwhelming military necessity. In December 1944, that calculation changed completely. On the morning of December 16, 1944, more than 200,000 German troops and nearly 1,000 tanks launched Operation Watch on the Rhine, Hitler's last desperate offensive in the West. The Germans struck through the Ardennes forest, aiming to split the Allied armies, capture the vital port of Antwerp, and force a negotiated peace before American industrial might became truly overwhelming. The offensive took the Allies by complete surprise. Intelligence had detected German build-up, but senior commanders dismissed the possibility of a major attack through terrain considered unsuitable for armor. Within days, German forces had driven a bulge 50 miles deep into Allied lines, surrounding the American garrison at Bastogne and threatening to reach the Meuse River. The weather was terrible. Heavy snow and thick clouds grounded Allied air power. German commanders felt relatively safe from artillery observation because poor visibility made accurate fire control nearly impossible. Forward observers could not see targets. Aircraft could not direct fire. The Germans believed they could move with relative impunity as long as the weather held. They were catastrophically wrong. On December 16th, the same day the offensive began, Colonel Oscar Alfred Axelson, commander of the 406th Artillery Group, faced an agonizing decision that would violate every security directive he had received. German forces were assaulting the 38th Cavalry Squadron near Monschau. The lightly armed cavalry desperately needed artillery support. They were being overrun. Axelson had just received a new type of ammunition, proximity-fused shells, codenamed POSIT. The rounds had arrived with explicit instructions. Eisenhower had not yet authorized their use over land. The security restrictions were still technically in place. Using them risked compromising technology that had been guarded more carefully than almost any other secret of the war. Axelson decided the emergency trumped the restrictions. He ordered his gunners to fire the proximity-fused shells. The effect on German forces was devastating beyond anything they had experienced in 3 years of combat on the Eastern Front. For the first time in the European theatre, American artillery was firing airbursts with perfect consistency, regardless of visibility or terrain. Each shell exploded 20 to 50 feet above the ground, precisely calibrated for maximum effect against personnel. The fragments spread in a cone-shaped pattern that covered an area 50 times larger than a ground burst. Foxholes provided no protection. Traditional defensive positions that had saved soldiers' lives since the First World War suddenly became death traps. The shrapnel rained down from above, penetrating even log-reinforced bunkers. German soldiers who had survived the meat grinder of Kursk, who had endured the nightmare of Stalingrad, who had seen every form of artillery bombardment the Red Army could deliver, had never experienced anything like it. They could not hear the shells approaching due to the high velocity. The first warning was the explosion overhead. There was no chance to take cover, no opportunity to seek shelter. The shell arrived and exploded before human reflexes could respond. The psychological impact was immediate and profound. On December 19th, 3 days into the offensive, General Dwight Eisenhower formally requested authorization to use proximity fuses without restriction. On December 21st, all limits were lifted. Proximity-fused ammunition was authorized for use in any theater, under any conditions, without restriction. Over the next 6 weeks, 200,000 proximity-fused artillery shells were fired in the European theater. Lieutenant General George Patton, whose Third Army was racing north to relieve Bastogne, later wrote to the War Department describing an action near the Sauer River. His artillery had caught a German battalion attempting to cross with a concentrated barrage of proximity-fused shells. By actual count, 702 enemy soldiers were killed in a single fire mission. Patton wrote that the new shell with the funny fuse was devastating. He predicted that when all armies had this weapon, they would need to devise entirely new methods of warfare. The morning of December 21st saw proximity fuses used in defense of Malmedy itself. SS Colonel Otto Skorzeni's Panzer Brigade 150 attacked the town at approximately 4:30 in the morning. American artillery battalions supporting the defense fired proximity-fused shells with devastating effect. The air bursts so unnerved the attackers that some German soldiers charged directly into American positions, seeking any shelter from the overhead explosions that seemed to follow them, regardless of how they moved or where they tried to hide. Prisoners captured during the battle provided American intelligence officers with insights into the psychological impact. One German artillery officer, captured in January 1945, described the proximity fuse as demonstrating a fundamental difference in industrial capacity between America and Germany. American engineering, he said, solved impossible problems through massive application of resources. Germany could never have produced such a weapon, he insisted, not because German engineers were less skilled, but because German industry could not support the required infrastructure. Another prisoner, a Luftwaffe engineer who had worked on German proximity fuse research before the program was cancelled in 1940, focused on the implications for air defense. If Germany had possessed proximity fuses in 1943 and 1944, he estimated the Allied strategic bombing campaign would have become unsustainable. But he immediately added a crucial qualification. Germany could not have developed the technology with available resources. The proximity fuse required an economy that could allocate billions of dollars to a single weapon system and mobilize over 100 factories to produce millions of units. Only America possessed such capacity. German soldiers experiencing proximity-fused artillery fire faced a more immediate revelation. They were being killed by technology they could not comprehend, produced in quantities they could not match, representing capabilities they could not counter. The Battle of the Bulge demonstrated how American artillery doctrine had evolved to maximize the fuse's effectiveness. Forward observers called down fire not just on visible targets, but on suspected positions. Artillery batteries laid down barrage patterns covering entire grid squares. The proximity fuses meant that every shell was an effective airburst. Every round that functioned, and 92% did, produced maximum casualties against any personnel within the fragment pattern. German tactical doctrine developed over years of warfare had to be completely rewritten in a matter of days. Traditional defensive positions were suddenly death traps. Concentrated formations were suicide. Moving in the open during artillery fire meant certain death. The Germans tried to adapt by dispersing more widely and staying constantly on the move. But adaptation had limits. Dispersion reduced combat effectiveness. Units spread across larger areas could not coordinate attacks. Communication became difficult. Command and control deteriorated. German soldiers began to exhibit what American intelligence termed artillery shock syndrome, a condition specifically triggered by the helplessness of facing proximity-fused fire. Officers reported that men who had fought bravely in other circumstances became paralyzed with fear when proximity fuses were mentioned. The syndrome resulted specifically from the realization that there was no defense, no tactic that could improve survival odds. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. American intelligence reports noted that German commanders were offering substantial rewards for intact proximity fuses, hoping examination might reveal weaknesses or provide insight into countermeasures. But German engineers never fully grasped what they had captured. Having concluded years earlier that radio-based proximity fuses were impossible given artillery acceleration forces, they never understood that miniature radio transmitters were inside every shell. The psychological block was complete. Because German scientists had proven proximity fuses were impossible, German intelligence officers could not believe that was what they were seeing. They looked at the evidence and interpreted it through the lens of their preconceptions about what was technically achievable. From January through March 1945, as Allied forces advanced toward the Rhine and into Germany itself, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe pilots reported shells that seemed to explode whenever they approached, regardless of altitude or maneuvering. What had been dangerous but survivable anti-aircraft fire became a nearly impossible barrier. During the Rhine crossing operations, American artillery fired tens of thousands of proximity-fused shells, creating such concentrated destruction that German defenders were unable to mount effective resistance. The Rhine barrier that German commanders hoped would delay Allied advance for weeks was crossed in days. General Eisenhower, writing after the war, acknowledged the contribution of the proximity fuse in stark terms. He stated that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe would have proven exceedingly difficult, perhaps impossible. The technical intelligence gathered from captured German documents after the war revealed the full scope of German proximity fuse research and the reasons it failed. German forces had indeed developed more than 30 different approaches between 1930 and 1940. Some were remarkably sophisticated, but none had advanced beyond limited testing by the time Germany cancelled the programs in 1940. When research resumed at Rheinmetall in 1944, hundreds of working prototypes were developed and test-fired, but by then it was far too late. Germany lacked the industrial capacity to set up mass production. Even if production facilities could have been established, the resources required would have competed with production of tanks, aircraft, submarines, and basic ammunition. The American proximity fuse program succeeded because it had resources that dwarfed the entire German military research budget. The proximity fuse alone consumed over $1 billion 1940s dollars. At peak output, American factories were producing 70,000 fuses per day. That represents nearly 9 billion individual electronic components manufactured to precise specifications, assembled, tested, and shipped to combat theaters around the world during the course of the war. The cost per fuse fell dramatically as production expanded. In 1942, each fuse cost $732. By 1945, mass production techniques had reduced the cost to just $18 per fuse. This 97.5% cost reduction resulted from systematic application of American manufacturing expertise. At $18 per fuse, the weapon was expensive compared to conventional ammunition, but not prohibitively so. A proximity-fused shell was worth 5 to 10 conventional shells in terms of target effect, since destroying an aircraft with conventional ammunition required dozens or hundreds of rounds. Using proximity fuses actually reduced total ammunition expenditure per kill, while dramatically improving effectiveness. The secrecy was so complete that production workers at different factories did not know other facilities were building the same components. The security classification remained in force until September 1945, when the war ended and the proximity fuse was finally revealed to the public. For German prisoners of war who had witnessed the defense against Von flying bombs while held in Britain, the revelation of what they had faced was profound. They understood that the same technology that had devastated their forces in the Ardennes was protecting British cities. Interviews with German soldiers conducted in 1946 after repatriation captured this understanding. 1. Former Wehrmacht officer described the proximity fuse as the weapon that finally made him comprehend Germany had lost the war. Not because of the fuse itself, but because of what it represented. The fuse was a solution to a problem that Germany had concluded was unsolvable. It required industrial capacity, scientific sophistication, and economic resources that Germany could not match even at the height of its power. If America could build miniature radios that fit inside artillery shells and worked after being subjected to forces that would destroy normal electronics, what else could they build? The officer's conclusion was that Germany had been fighting a war of the 20th century, with 19th century assumptions about what was possible. When told something was impossible, German engineers documented why it could not be done. American engineers figured out how to do it anyway. The proximity fuse demonstrated multiple technological advances that extended far beyond the immediate military application. Miniaturized vacuum tubes required breakthroughs in material science. The reserve battery design using centrifugal activation was genuinely innovative, but perhaps the most significant advance was in manufacturing and quality control. Producing millions of complex electronic devices with consistent quality required systems and processes that barely existed before the war. American industry developed statistical quality control methods that ensured production consistency. Workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training. James Van Allen, the physicist who helped develop the ruggedized vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite, launched in 1958, used instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. Engineers who had worked on proximity fuses went on to careers throughout the electronics industry, bringing expertise in miniaturization, quality control, and mass production. Workers trained in precision assembly became the workforce for television manufacturing, radio production, and early computer assembly. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions. Modern weapon systems use descendants of the World War II proximity fuse. The Patriot surface-to-air missile uses proximity fuses that can operate in intense jamming environments. Modern artillery shells use proximity fuses that can be programmed before firing to detonate at specific altitudes. Today's fuses use solid-state electronics instead of vacuum tubes. Microprocessors replace the analog circuits, but the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, trigger the warhead for maximum effect. Post-war analysis by military historians identified the proximity fuse as one of the key technological advantages that shortened the war in Europe and the Pacific. Against kamikaze attacks in the Pacific, proximity fuses were credited with preventing ship losses that would have significantly delayed operations. The Okinawa campaign would have been far more costly without proximity fuses protecting the massive fleet offshore. The strategic impact was multiplied by production scale. Because fuses were available in effectively unlimited quantities by late 1944, they could be used without conservation. Fire missions that would have been questionable with conventional ammunition became routine. Suspected enemy positions could be saturated with fire. The psychological effect of this abundance was as significant as the physical effect. German and Japanese forces came to understand that America possessed weapons in quantities they could never match. Every artillery barrage used proximity fuses. Every ship mounted 5-inch guns with proximity-fused ammunition. Every defensive position faced air bursts that made traditional cover useless. The story of the proximity fuse is ultimately a story about resources, priorities, and the different paths nations took through World War II technology development. Germany invested heavily in advanced weapons like jet aircraft and ballistic missiles. These were impressive technical achievements that demonstrated German engineering prowess, but they came too late and in too few numbers to affect the war's outcome. America invested in technologies that could be mass-produced immediately and would provide decisive advantages in current operations. Proximity fuses, while sophisticated, were designed from the start for mass production. Every decision in their development prioritized manufacturability and reliability over theoretical performance limits. This reflected a fundamental difference in strategic thinking. Germany sought war-winning superweapons that would offset Allied numerical superiority through technological excellence. America sought effective weapons that could be produced in quantities that made numerical superiority overwhelming. The Sherman tank was not superior to the Tiger, but America produced 50,000 Shermans. The proximity fuse was not magic, but America produced 22 million of them. That approach proved decisive. In the final accounting, the proximity fuse represented everything that made American industrial power dominant in World War II. It combined advanced technology with practical engineering. It required massive investment but produced proportionate results. It was sophisticated yet manufacturable, effective yet affordable at scale, innovative yet reliable enough for mass deployment. The German soldiers who faced proximity-fused fire understood this implicitly. Wehrmacht veterans interviewed after the war consistently described the fuse not merely as a clever weapon, but as a demonstration of comprehensive superiority in science, industry, and national will. The proximity fuse ended their war not through any single dramatic defeat, but through the accumulated weight of countless engagements, each proving the same lesson. They were fighting an enemy with capabilities beyond their ability to match or counter. That realization, more than any battlefield loss, broke the Wehrmacht's spirit and hastened the end of the Third Reich. The Japanese experience was similar, though manifested differently. Japanese pilots and sailors faced proximity-fused fire throughout the Pacific War without understanding what made American defenses so devastatingly effective. Post-war interrogations revealed that Japanese military leadership never fully grasped the technological advantage America had achieved. The idea that individual shells carried autonomous targeting systems seemed beyond credible possibility. This failure of imagination allowed the proximity fuse to remain operationally secret even after millions had been expended in combat. The Japanese concluded that what seemed impossible must not be what was actually happening. They looked at the evidence and rejected the correct interpretation because it contradicted their understanding of technological limits. The weapon that had seemed impossible to build became the weapon that changed warfare forever. American scientists, engineers, factory workers, and military personnel had accomplished what the world's experts declared could not be done. They had miniaturized complex electronics beyond what was thought possible. They had made delicate vacuum tubes survive forces that should have destroyed them. They had manufactured the result by the tens of millions. The proximity fuse stands as testament to what free societies can achieve when they combine scientific excellence with industrial might and unwavering determination. It proved that the greatest victories come not from seeking the impossible, but from making the necessary possible through sheer force of will and unlimited application of resources. This was America's triumph in World War II. Not individual brilliance, though brilliant individuals contributed enormously. Not just industrial capacity, though capacity was essential, but the combination of scientific method, engineering pragmatism, industrial scale, and democratic values that allowed a free society to outthink, outproduce, and ultimately overwhelm enemies who had started the war with apparent advantages. The proximity fuse, those 20,000 G-rated fuses that turned 5-inch guns into plane killers at 3 miles, represents this synthesis perfectly. Technology that seemed impossible became routine. Costs that seemed prohibitive became acceptable. Production that seemed unachievable became reality. And in the end, the shells that exploded themselves at precisely the right moment to kill enemies who never understood what killed them proved that American ingenuity, combined with American industry, created weapons that won wars and changed history. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.